fluid friction loss calculation. For this problem, you have to think kind of backward in solving this problem. For example, the final step of the fluid friction loss calculation is to apply the Bernoulli's law or the energy conservation law between point 1 and point 2. Like here it is written there. So all the energy at point 1 in terms of elevation energy, pressure energy, velocity head, if there is any pump adding any energy to it, any motor taking the energy, and the losses. So we don't have any pump here or motor here. So all the energy at point 1, no elevation energy because they're sitting in the same elevation, so G1, G2 same. Also, they're the same pipe size, so there is no velocity head either. So the only thing you need to worry about is the pressure head at point 1, which is P by gamma, minus the loss between point 1 and 2, and whatever left, that will be available at point 2. So the loss, this is the piece that we're trying to calculate in this problem. To calculate losses, you need to find out the friction factors, because the formula to calculate losses, the Darcy's equation has a friction factor in it, so which is the head loss is equal to friction factors times L, the length of pipe, divided by the diameter times the velocity head, p squared by 2z. To find the friction factor, you need to know the flow type, because there are two formulas for that. For laminar flow, if the flow is laminar, then you use friction factor formula is 64 by NR, the Reynolds number. For the transition flow, if turbulent or transition, turbulent flow, you need to use the turbulent flow. You need to use the Moody diagram to find the friction factor. And both for Moody diagram and for laminar equation, you need the Reynolds number, NR, which is the second step. To find the Reynolds number, it has velocity in it, so you have to find out the velocity too. So first you have to find the velocity, then Reynolds number, flow type, and all these steps. So let's go ahead and work on this problem. So the velocity, that's the step number 1, velocity. To calculate velocity, we have the flow rate given, which is 50 gallon per minute. In this problem, you can go back and see, say 50, oh no, that's a 10 gallon per minute flow rate, 50 psi at point 1. So the flow rate is given, so we can write that equation, continuity law, Q is equal to area times the velocity. So flow rate given 10 gallon per minute. I'm going to convert that gallon per minute here. So 1 gallon is 231 inch cube. And then I'm going to convert that minute to second. 1 minute is 60 seconds. Then we'll do area is pi by 4d square. It's a 3/4 pipe, 3/4 inch pipe times the velocity. Now from here, the velocity will come in inch per second. As you can see here, this inch cube and inch square will cancel. So this minute cancel, gallon cancel, inch square will cancel, inch square there, and you still have inch left and second left. So there will be a number here. Then you have to convert that inches to foot. So 12 inches is 1 foot. If you perform all these calculation correctly, I found 7.26 foot per second for the velocity. For the Reynolds number equation, I can use their few Reynolds number equation. So this is my step number 1. Step number 2 is the Reynolds number. The one that I can use is this 77401. So in that one, velocity is in foot per second. Then if the diameter is in inches, and then the viscosity given in centistroke, the prime is given in centistroke in this problem. So I can plug all these numbers here. So 7740, velocity I calculated 7.26 foot per second. Then diameter is a 0.75 inch diameter pipe. Divide by the viscosity, I think, is given in 1 centistroke in the problem. So the Reynolds number I calculated was 42,157. It's a dimensionless number, so it doesn't have any unit. So if the Reynolds number, step 3 is to determine the flow type. So if the Reynolds number is more than 4,000, then the flow is considered turbulent flow. For the turbulent flow, we have to use the Moody diagram to calculate the friction factor or find the friction factor. So we're going to go to the Moody diagram. So this is the Moody diagram. To find the friction factor from the Moody diagram, we need to find out the relative roughness of the pipe. So this is a high density polythene pipe which has a roughness of 0.0084, and then you have to divide that by, so this relative roughness is 0.00084 divided by 0.75 inch, which is the diameter of the pipe, and that I found 0.0011 relative roughness. So this line here, we have to follow this about 0.001, this line here. Before that, I want to draw a Reynolds number line. So we calculated 42,000. This is a log scale. So this one is 10,000, this point 20,000, 30,000, 40,000. So the line I draw here is about 42,000. And then we have to follow these 0.011 just over that. So this is the line. It's not straight, so I'm going to follow this solid line. So this is where it meets that. Then you have to draw another line to the left, like this one. So that gives us 0.025 friction factor value. You don't have to be precise, just close enough is good. Now we're going back to the problem there. So the friction factor we found from the Moody diagram was 0.025. So the next step is to calculate the friction losses. Now, friction loss calculation, in this problem, we have total 100 feet of pipes within the house, plus you have 150 feet garden hose, plus you have 5 elbows and 2 gate valves. So you have to account for friction losses for all of them. The easier way to calculate the friction factor for the fittings is to think about the equivalent length concept. Equivalent length LE is KD by F. The idea of equivalent length is the total amount of loss for a straight pipe. So how many feet of a straight pipe has the total amount of loss of these 7 fittings? 5 elbows and 2 gate valves. So, and then you find the equivalent length, and then you add this with the other 2 pipe lengths. One is within house 100 foot, and then the garden hose is 150 feet. So to calculate this, the total, so for the wide open gate valve, you can find the K value, the constant value for that. This is where you can find if the gate valve is wide open, the K factor is 0.19. And then you have elbows. The elbows are given 90-degree elbows, so that K factor for 90-degree elbows is 0.75. So simply what you can do is you can add this total. So you got 5 90-degree elbows times 0.75 plus 2 wide open gate valve. So that's the total constant factor. And then the diameter of the pipe is 0.75 inch divided by F friction factor, which is 0.025. Now this will come in inch, so you have to convert that to foot. 12 inch is 1 foot. So I calculated the equivalent length is 10.33. Is it? Let me see. Yeah, 10.33 foot. So 5 90-degree elbows and 2 gate valve will have exact same loss as 10 foot of straight pipe. So the total loss you have to account for is that 100 plus 150 plus that equivalent lead 10.33. So if you add all of them, it's 260.33. Probably can ignore the numbers after the decimal point. So this is the total foot of equivalent length we have to account for, or total length we have to account for the friction. Now the friction loss formula is the friction factor times L by D times V square by 2Z. So friction factor is 0.025 times L, which is the 260. 0.33, probably not gonna make any difference. 0.75 inch is the pipe diameter. I need to convert that. I'm gonna convert it right here. 12 inch divided by 1 foot times V square by 2Z. I think the velocity we calculated 7.26 foot per second. Then 2 gravity constant 32.2 foot per second is square. If you do all of these calculate correctly, I found the total loss is 85.28 feet of water. Now this is pressure head in terms of water head. So I can calculate this into PSI using this P equal gamma H equation. So the water gamma is 62.4 pound per feet cube times this H, 85.28 feet. Now this will give me pound per feet is square. Then I have to convert that to 1 foot is 12 inch, whole square that. So this will produce me in PSI. So P, total pressure loss, I calculated 36.95 PSI due to the pipe and fittings. if we go back to the Bernoulli's law, the first page right here. So in here, we calculated. So you can simply, this is in pressure head equation, but here we had 50 psi, and total pressure loss we calculated between 0.112 was 36.95 psi. So at 0.2, that will be available after the loss. So this is 0.1, 50 psi minus the loss. So that will be equal to pressure at 0.2. So that is only 13 psi will be available at 0.2.